Hey, this is Mrs. Johnson. This is MAT 221. We're in Calculus 1, Section 2.7. We're talking about the derivative as a function. We last talked about sketching derivatives. Now I want to talk about the derivative of the derivative. Being that I have a function, and that function could now have slopes of its own, we can find what's called higher derivatives, or second, or third, or fourth derivatives. So if a function f is differentiable, then its derivative f prime also is a function, and so f prime can have a derivative of its own. It's denoted by the derivative of the derivative, or f double prime. This new function f double prime is called the second derivative of f, because it is the derivative of the derivative. Now this is down here, f double prime is Newton's notation. Leibniz used this notation, which was the derivative with respect to x of the derivative of y with respect to x, which brought him to this notation. So if you see this notation, it simply means the derivative of the derivative, or the second derivative function. So the graphs of f prime, and f double prime are shown. Now you can see that the original function is the blue function. Notice it's a cubic function. Its derivative ends up being a quadratic, that's right, and its derivative, the second derivative, ends up being a linear. Now this will be true for all polynomial functions, that they will drop down a power. But we're not only going to be studying polynomial functions, we have lots of different functions. But I do want you to notice some things about the functions and how they're related. Notice where the tangent line to the blue curve is horizontal, like right about here. Notice the derivative curve is 0 there. Again, because the derivative gives the slope of the function who it's the derivative of. Here where the the slope of the tangent line is again horizontal, notice the derivative curve hits the x-axis there, is equal to 0, because the derivative is the 0 at this x value. The blue curve has a derivative of 0. Notice also at the point of inflection, where the curve is decreasing the fastest, or the most negative slope, is where the derivative curve is turning. Notice that. I have the most negative right there. Now if we look at the green and red curves, notice where the derivative curve has a slope of 0 at x equals 0. The second derivative now has a root, or a 0. Notice where the first derivative has positive slopes, the second derivative is above the x-axis, and where the first derivative has negative slopes, the second derivative is below the x-axis. Again, what we did earlier will follow through just as we go through, where the derivative is the slope of the curve that we're looking at. In general, we can interpret the second derivative as the rate of change of the rate of change. The most familiar example of this is acceleration, which we define as follows. If s of t is the position function of an object that moves in a straight line, we know that its first derivative represents the velocity, v of t, of the object as a function of time. So, as we refer to some physics problems in the future, remember that the velocity function is the first derivative of the position function, sometimes denoted as ds dt. The instantaneous rate of change of the velocity with respect to time is called the acceleration, a of t, of the object. Thus, the acceleration function is the derivative of the velocity function, and therefore the second derivative of the position function. So, the acceleration function is always thought of as the derivative of the velocity function, or the second derivative of the position function. If we use Leibniz notation, acceleration equals the derivative of velocity or the second derivative of position. The third derivative is the derivative of the second derivative. It's denoted by f with 3 primes. So f triple prime can be interpreted as the slope of the curve, f double prime, or as the rate of change of the second derivative. If y equals f of x then has alternate notations here for the third derivative, this is also the third derivative. This means the third derivative. This means the derivative of the second derivative, or this is Leibniz notation for the third derivative. The process can be continued on and on and on and on until we don't have any derivatives anymore, which sometimes will never happen. Some of them are cyclical and will have a derivative forever. The fourth derivative is usually denoted by this. Instead of continuing to write primes, we usually go and just say f4, meaning the fourth derivative. In general, the nth derivative of f is denoted by f with parentheses n, and this is obtained from how many times you're differentiating. For instance, if you wrote f to the parentheses 10, that would be the 10th derivative. So we would write it like this: y to the n, y to the nth derivative, f nth derivative, the nth derivative with respect to x. We can also interpret the third derivative physically in this case where the function is position of the object. It is called the derivative of acceleration, or the third derivative of position. This function is called jerk. Jerk is given as the derivative of acceleration, the second derivative of velocity, and the third derivative of the position function. That wraps up section 2.7 for now. However, I will be putting up some videos going through some of your worksheets. Please look at your worksheets in the worksheets folder and work on some of those to help you to be able to sketch the derivative. Now, what I'm going to do here in these next couple of minutes for section 2.7 is I want you to go to your web links page in your course content in your week 5 folder, and then look at the web links there. And there's a couple of different things here that will help you when we're trying to learn how to sketch the derivative. This first thing I think I already used in our last video, which showed the secant line and the tangent line to the curve. I don't know if I actually did this with you or not, but this is a GeoGebra. You can see this is actually showing the tangent line to the curve at a given point. And you can see this is the secant line between 2 points. And we know that as the 2 points get closer together and closer together and closer together, we know that the secant line and the tangent line almost look identical to each other. So if you look at this, if we moved this point, the tangent line to the curve here, I'm sorry, I'm going to move C, not C plus H, you can see how the tangent line moves across the curve. As you move the point across the curve, you can see. And if you notice, this also tells us the value of C and the value of H in this particular case. But it shows you here how once I get to that sharp corner that we talked about earlier, there is no derivative, there's no tangent line because I can't find the slope there. But over here I can notice it's really negative slope, then it turns to a positive slope, really positive. And now as you notice, the derivative gets less and less and less and less as it comes towards 0, and so forth. So I wanted to show you some of these web links that I have. This one is a GeoGebra that will actually trace the derivative for you. So you can enter any function you want in here, and then you can drag point A, and it will sketch the derivative curve for you. Now notice if I start right here, the slope of the curve is positive. And notice it's plotting a point up here. So when x equals 2, the value of the derivative is a positive value. It looks like almost like positive 10. Now I'm going to show you, as I take this curve and I drag a, notice the derivative is less and less. They're all positive numbers. Notice they're positive numbers, but notice less and less. It's actually telling you what the slope is here. The slope is 2.58. Now it looks like when I get here at like 0.8 or so, I should have a 0 derivative right about there. And you notice I do. Notice a 0 derivative. If I move my point this way, notice these are all positives, and it gets more and more and more positive as I go this way. And then I hit 0. And then if I look over this way, now I have a negative tangent line. Notice the derivative is being below the x-axis. I'm sorry, I lost my point there. Notice my derivative is below the x-axis because these are negative slopes. And so at x equals 0, looks like I have a slope of like -2, so I should plot the point 0, -2. Notice that's what's being plotted on my derivative graph. Looks like I should have another 0 somewhere over here at like -0.9 or so, -0.8 or 0.9 or so, right? Looks like I should have a 0 point there. So this is actually showing you, it's sketching you the derivative for you. That green sketch that it's sketching is sketching your derivative for you as you sketch the graph. So there's your derivative of this particular graph. Now, this is nice because it actually helps us see what different graphs look like, what the derivative graph would look like. The only thing is we have to have the skill ourselves to do these by hand. We should be able to sketch these. Again, they don't have to be perfect, but the things I will be looking for is where the curve has a horizontal tangent line, you should be hitting the x-axis on your derivative. Horizontal tangent line, you should be hitting the x-axis. Where the curve has a point of inflection, in this case negative, that should be the most negative point on the curve. And where the slope is positive, your derivative should be above the x-axis. Where the slope is positive, again, the derivative should be above the x-axis. And where the slope is negative, notice from this point to this point, the slope is negative, so notice the derivative curve lies below the x-axis. Those are key things that we're going to look for. You can change the graph, by the way. You can change the function and then play with this a little bit in your web links folder. Here's some other things to do to help you for sketching the derivative. This one actually, when you execute it, it brings you to an Excel file, which helps you to see what these look like. I'm going to open it up in Excel. It clicks down here. And what's really cool about this thing is it lets you kind of guess which of these three is going to be your derivative. So what you do is you start here with the slider, and you start sliding the curve over a little bit like this. You start sliding values of x. I could just go like this. So this is the original function. The original function is starting to look like this. One of these three is the derivative of this function. Now, notice, I'm going to guess right now, look, you can see that the curve is rising, f of x is rising. The derivative would be positive, which means my derivative has to lie above the x-axis. So I'm going to cross out p. P cannot be my derivative here because it is lying below the x-axis. If I keep on sketching this curve, and my curve looks something like this, okay, which of the other two is my derivative? Well, my derivative looks like it's horizontal right about here, so I should have a 0 point, which I have on both of these 0 points. But then the derivative is positive again, so the derivative is positive again. G of x must be my correct derivative. play with these and see how you